class, we're going to talk about how we hear. So first, before we get into all the sensation, we're going to talk about how our brain, our body, transforms sound waves into neural impulses so that we can hear. So the first step is the sound waves coming to our eardrum, right? In the outer ear, the very outer ear, but also sound waves into the eardrum. Second, because sound waves have vibrations, the bones of the middle ear amplify and relay the eardrum's vibrations into cochlea, and the pressure in the cochlea water, it changes, which makes basilar membrane vibrate. It makes it vibrate, ripple, and it makes the hair cells to bend. And the hair cells are directly connected to the nerves in the brain. So when hair cells bend, neural impulses are directly sent to our brain to interpret as sound waves. Interpret as neural impulses as auditory cortex.
Hi guys, I'll talk about frequency, amplitude, and sound waves. Frequency is the number of complete wavelengths that pass a point in a given time. For example, 5 wavelengths per second. If frequency is high, the sound have a high pitch. Like this, the sound wave of a bass guitar has a long wavelength and a low frequency, so it has a high pitch.
You're wrong. It's actually low frequency equals low pitch.
And the sound wave of a whistle has short wavelengths and high frequency, so it has a high pitch. Loudness depends on the amplitude or height of the sound wave. The greater the amplitude, the louder the sound we perceive. Amplitude is measured in decibels. The absolute threshold of human hearing is defined as 0 decibels. Amplitude is the loudness of a sound. Sound waves are changes in pressure generated by vibrating molecules. A sound wave is the pattern of disturbance caused by the movement of energy traveling through a medium, such as air, water, or any other liquid or solid matter. As it disperses away from the source of the sound, the source is some object that causes the vibration, such as ringing telephone or a person's vocal cords. The vibration disturbs the particles in the surrounding medium. Those particles disturb those next to them, and so on. The patterns of the disturbance creates outward movements in the wave pattern, like waves of seawater of the ocean. The wave carries the energy sounds through the medium, usually in all directions, and less intensely as it moves farther away from the source. Bye.
The outer ear. The outer ear is the part where it is attached to our face, and it consists of pinna or auricle and the ear canal. The pinna. It is the part of the ear that we see on each side of our heads. It is made out of cartilage and soft tissues so that it keeps a particular shape but also flexible. The pinna serves as a collector of sound vibration around us and guides the vibration into our ear canal. It helps us decide the direction and source of sound. The middle ear. The middle ear begins with the eardrum at the end of the ear canal. The middle ear contains 3 tiny bones called the hammer, anvil, and stirrup. These 3 bones form a connection from the eardrum to the inner ear. As sound waves hit the eardrum moves back and forth, causing the ossicles to move. As a result, the sound wave is changed to a mechanical vibration.
So the eardrum transmits sound from the ear to the ossicles inside the middle ear and then to the oval window in the fluid-filled cochlea. So, I will explain the bones of middle ear. Sound enters the outer ear. This strikes against the eardrum and makes it vibrate. These vibrations go via the eardrum to the ossicles. Hinges connect the bones, and they form a lever system, and the sound is transmitted to the stapes. This pushes like a piston against the membrane in the oval window of the inner ear. Thus, the sound vibrations from the drum are carried to the inner ear. The lever is actually adjustable by the muscles in the middle ear and may actually dampen very loud sounds to protect the inner ear. The oval window or vestibular window is a membrane-covered opening which leads from the middle ear to the vestibule of the inner ear. Vibrations that come into contact with the tympanic membrane travel through the three ossicles and into the inner ear.
The inner ear. The inner ear is also called the labyrinth of the ear. The inner ear contains the sensory organs for hearing and balance. The inner ear contains three sections: the vestibule, the semicircular canals, and the cochlea. Semicircular canal. This structure helps control one's sense of steadiness or balance. These balance organs share the temporal bone space within the cochlea. These organs also share the same fluid that is in the cochlea.
So the function of the cochlea is to transform the vibrations to the cochlear liquids and associated structures into a neural signal. This occurs at the organ of Corti, which is located all along the cochlea.
The basilar membrane within the cochlea of the inner ear is a stiff structural element that separates two liquid-filled tubes that run along the coil of the cochlea. The auditory nerve. The auditory nerve is a bundle of nerve fibers that carries hearing information between the cochlea to the brain.
Bar, 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 bar. The audio is actually the same. Take turns looking at the different pictures on the next slide. Bar, 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 bar.
So, how do we perceive loudness?
So, loudness. How we perceive loudness is very, very simple. So if you hear soft tones, only one or a few hair cells on our basilar membrane vibrate, only one soft sound. While when you hear very loud noise, the neighboring hair cells also vibrate, not only one, which sends more impulses to our brain, saying that the sound is very, very loud. So, there are two theories explaining how we perceive pitch. The first theory is called place theory. Now, it says that when high pitch is heard, our cochlea membrane, the beginning part of the cochlea membrane vibrates, and it responds to high pitches, sending neural signals to our brain. And when we hear low pitch, then the end part of the cochlea membrane vibrates, and it's a neural signal saying that it's a low pitch. However, the place theory is flawed because there isn't a specific part in the cochlea membrane that really responds to low. It's all over the place, not really at the end. So it really explains how we hear high pitch. And the second theory, called frequency theory, is it says that when you hear high pitch, the frequency speed is triggered as neural impulses, which sends impulses to our brain saying that it's high or low. So the faster the pulse is, the higher the pitch is. However, in our hair cell, one hair cell cannot send more than 1,000 beats per second. So, which is only the third octave in the piano. So this isn't really high. So it is flawed because we can't hear higher sounds than third octave in the piano. And that's when the volley principle comes in, which says that not only one cell has to vibrate, but other cells can vibrate in the membrane, which can add up to more than 1,000 frequency per minute per second, which can help us hear. So frequency theory really explains how we hear low pitch, while place theory explains how we can hear high pitch.
So good morning, class. Since today Miss No is sick, I'm taking over your class. So today we're gonna learn how we locate sounds. So we receive more intense sounds on our right ear than our left ear. And we humans have hard time receiving sounds from ahead, above, behind, and below. This is because our both ears receive sounds simultaneously.